Okay, good morning, children. So, yesterday where we left, it was how to use bond enthalpy data to calculate the enthalpy of reaction. So, here I am giving a question on that. Using bond enthalpy value, how can we calculate the enthalpy of reaction? Suppose a reaction. Suppose nitrogen gaseous plus hydrogen gaseous arrow NH3 gaseous, and we have to balance this. Suppose in the question it will be given in the balanced form. So 2 and here 3. So for this reaction you are asked to calculate the uh, standard enthalpy of reaction. This you are asked to find. What are given to you? Will be given bond energy values. Bond energy values. Which bond energy values we require? We can understand if I write this equation in another form. Now, nitrogen is N triple bond N, gaseous. Hydrogen is single bond, gaseous. And ammonia is like this, gaseous. So we need N triple bond energy, we need H single bond energy, we need NH single bond energy. Okay, now these bond energy values will be given to you in the question. Now for the time being, we are using it from the bond enthalpy table. Okay, in the bond enthalpy table we have N triple bond N. It is 946 kilojoules per mole. H single bond H value, it is 435.8 kilojoules per mole. These are all kilojoules per mole. And N single bond H, this bond energy is found to be in the table 389 kilojoules per mole. So this I have got it from the table. You should try yourself try to find out from the how to read this table that I have said you the other day. Okay. Now since it has been said enthalpy of reaction, standard enthalpy of reaction, it is summation of bond enthalpy of reactants minus summation of bond enthalpy of products. It was said like this. So reactants, we have nitrogen triple bond, so here we have to write 964 plus then hydrogen it is 435.8. Now since here 3 is the coefficient, this value we have to multiply by 3. This value we have to multiply by 3, so we have written for the reactants. Now coming to the products NH bond energy is 389. So you see 3 bonds and then again 2 here, 3 into 2, 6. So it will be 6 into 389. So you simplify this and you get the answer. So in this way, using bond enthalpy value, we can find out standard enthalpy of reaction. Okay, now uh, we are going to discuss uh, your Born-Haber cycle. Born-Haber cycle. So, what is Born-Haber cycle? That I'm going to discuss now is suppose we consider the formation of sodium chloride. Let us consider the formation of sodium chloride from its element. From its constituent element. You know, for sodium chloride, the constituent element is sodium and chlorine. Okay, so sodium chloride, which is solid, is being formed from its constituent element. Constituent element is sodium. Sodium is physical state is solid. Then chlorine. Chlorine is a constant element. Chlorine is gaseous. And since here we have 1 mole of 1 Cl, so to make it balanced, we have to write here half. So 1 mole of sodium chloride is being formed. So you know this enthalpy change, according to definition, this is enthalpy of formation. Enthalpy of formation. Now this process, you know, can be thought of being carried out in some other way that I am showing you here. Sodium solid to sodium gas. Now you already know solid to gas. Now it is called sublimation. So here sublimation enthalpy is involved. Sublimation enthalpy. Then suppose sodium gaseous. Now since you know sodium chloride is actually Na plus Cl minus. Sodium chloride is Na plus Cl minus. So that's why we consider this process Na gaseous to Na plus gaseous. Na gaseous to Na plus gaseous. Now what is this process? It is called ionization enthalpy. So delta H ionization enthalpy. Okay. Next, here we are considering this process because we need chloride ion. So first of all, the bond that is there, that has to be broken. So after the breaking of that bond, it will become Cl gaseous. So this Cl2, it is in molecular form having a bond. That bond has broken. It became Cl gaseous. It is in atomic form now. And what will be the enthalpy involved? It is dissociation enthalpy. Dissociation enthalpy we can say. And since here half mole is involved, so here actually half of dissociation enthalpy will be involved. You know, this can also be called, if you want to say it in another way, since from molecule to atom is formed, it is also called enthalpy of atomization. We can call it enthalpy of atomization. Then Cl gaseous to Cl minus gaseous, you know, electron is gained, and here enthalpy is called electron gain enthalpy. Electron gain enthalpy, and now this sodium ion and chloride, you know, they will combine and they form sodium chloride solid. And enthalpy change here in this step, this is called lattice enthalpy. This is called lattice enthalpy. So what is the definition of lattice enthalpy? Lattice enthalpy is when 1 mole of ionic compound, is formed from its constituent ions, in the gaseous state, then enthalpy change is called the enthalpy of reaction. So this is the cycle. Now let me first tell you about one law. Then I will again come back to this. That is Hess's law of constant heat summation. Hess's law of constant heat summation. So what is this law? Suppose we have a process A to B. We have a process A to B, and suppose this process, enthalpy change involved is delta H. Now, if we think of carrying out this process, in another path, suppose A to C first, C to D next, and then from D we get B. So same change we are bringing about in say 1, 2, 3 steps. In 3 steps, and suppose the enthalpy change here it is delta H1. The enthalpy change here it is say delta H2. The enthalpy change here it is say delta H3. Now, since we know enthalpy change is a state function, enthalpy change does not depend on path. So, enthalpy change if we go from A to B, or enthalpy change, rather some of the enthalpy change if I go from A to C to D to B, will be same. So what we can write here is delta H will be equal to delta H1 plus delta H2 plus delta H3. That we can write, and this is only what is known as Hess's law of constant heat summation. So the statement of Hess's law will be what? If a process is carried out in multiple steps, then sum of the enthalpy changes at each step will be equal to the enthalpy change if it is carried out in one step. Now, if we apply this Hess's law of constant heat summation in this Born-Haber cycle for sodium chloride, so certainly we can write this thing. So you see, this is carried out in one step, and these are in multiple number of steps. So we can write here delta HF will be equal to delta H sublimation plus delta H ionization enthalpy plus delta half delta H dissociation enthalpy plus delta H electron gate enthalpy plus delta H lattice enthalpy. So this we can write from Hess's law of constant heat summation, and the importance of this Born-Haber cycle is that if all the data, all these values are known to us, say except one, then we can find out that particular enthalpy. Suppose we can find out from this, the electron gate enthalpy we can find out, or we can find out say lattice enthalpy we can find out, provided other values are known to us. So this is the importance of Born-Haber cycle. Now I am giving you one question for yourself. Suppose I have drawn Born-Haber cycle for NaCl. You should try to do Born-Haber cycle of magnesium oxide. Magnesium oxide. Now magnesium oxide, since it is Mg plus 2 O minus 2 minus 2, and just I'm giving you a hint here. There will be for magnesium ion formation, two steps, i.e. first ionization enthalpy and second ionization enthalpy will be there. Similarly, since O it is minus 2, here also there should be two electron gain enthalpy. First electron gain enthalpy and second electron gain enthalpy. Those steps should be there. So this is what is known as Born-Haber cycle. Now we will be taking up this topic now, your spontaneity of a reaction. Okay, so we take up this topic, N-E-I-T, spontaneity. I hope you know the meaning of spontaneity. In nature we see so many processes taking place, and they are a spontaneous process. For example, flow of water downhill. This is spontaneous process. Water keeps on flowing. Suppose in a river, water keeps on flowing all the time. So flow of water in a river or flow of water downhill is a spontaneous process. Similarly, say wind blows. If there is difference in pressure, the wind blows, and that is also a spontaneous process. Similarly, say we have a cup of tea. It's hot. Now it will continuously lose heat. It will continuously lose heat, and its temperature will go down. That means a hot body continuously loses heat. So that the flow of heat from higher temperature to lower temperature is also a spontaneous process. So in this way there are many processes in nature which are called spontaneous process, and likewise there are processes also which does not take place on its own. We have to supply energy from outside, then only that will take place, and those processes are called non-spontaneous process. Non-spontaneous process. Suppose flow of water up the hill. Flow of water up the hill cannot take place. If we want that to take place, we have to supply energy. We have to supply force. Then only water will flow uphill. So flow of water uphill is non-spontaneous process. Now spontaneous process, can be divided into two. Spontaneous process or spontaneity are of two types. There are spontaneous process without initiation, and there are spontaneous process which requires initiation. So there are a spontaneous process of two types, one which requires no initiation and one which requires initiation. Let me explain this too. Suppose we have we take the case of burning of fuel, say burning of petrol or burning of diesel. Now here initiation is required, a spark, a little bit of fire is required, and once it starts burning petrol, diesel, then it keeps on burning. So that is a spontaneous process which requires initiation. Now, as I said, flow of water, flow of air from high pressure to low pressure, these are all spontaneous process without initiation. So now the question is, when we have spontaneous process, when we consider spontaneous process, so what is the driving force that we need to find out? What is the driving force? If a process happens spontaneously, maybe without initiation or with initiation, there must be some agent, there must be some force which is actually doing it. We need to find out the nature of this driving force. Now, before we find out the nature of driving force, let me introduce another state function. Let me introduce another thermodynamic state function, which is called entropy. Entropy, whose symbol is S. And what is entropy? Entropy is, it is measure of randomness of a system. It is a measure of randomness of a system. For example, we have, say, three systems. We have three systems. Here we have, say, ice. Here we have water. And say here we have water vapor. Water vapor. Here the molecules of water, they are, how they will be. The molecules of water here will have some movement. And here the molecules of water will have the maximum movement. So randomness is more here. Next it is here, and here the randomness is very less. So we say that entropy of this system is more than this system. Entropy of this system is more than this system. So we can straightway write, entropy of solid will be less than entropy of a liquid, which is less than entropy of gas. Okay, now suppose I am giving some process. You have to predict the change in entropy. You can predict the change in entropy. Suppose this process, H2O liquid to H2O gas. So during this process, what will be the change in entropy? Whether the entropy will increase or decrease. Say another process, say calcium carbonate solid to calcium oxide solid plus CO2 gas. So during this process, what will be the entropy change? Say finally, we have say this process, say this H plus aqueous plus OH minus aqueous, forming H2O liquid. So what is the entropy change for this? Now let me first tell you about this process. Say here we have in the final we have we have gas. Definitely this entropy will be more than this entropy. So entropy change, since entropy is increasing, the entropy change, entropy change, we can write it like this: entropy change. Entropy change, which is again final minus initial. So since final is more, so entropy change will be positive. What about for this process? Here we have solid. Solid has very less entropy. This is also solid, very less entropy. But since in the product side we have a gaseous component, gaseous component will have more entropy. So for this entropy change, will be positive. Entropy, if this process happens, entropy of the system will increase. And what about this? What about this? You see, it's aqueous. It's also aqueous. In aqueous state, the ions will keep on moving. Here, randomness is more. Ions, moves very much. Whereas here it is water. Water, randomness will be comparatively less. So here entropy change will be negative. So you may be getting questions like this, and you will be asked to predict the entropy change. Now to end today's class, let me define entropy change. Define entropy change. Suppose a process is taking place A to B. What is the entropy change for this process? If it is delta S is defined as heat change taking place during the process in a reversible manner. Heat change taking place in reversible manner, reversible process, divided by the temperature at which the process is taking place. This temperature will be in Kelvin. So this is a definition of entropy change, and you can understand from this term the unit of entropy change in SI unit. It will be, since it is energy, it will be joules per Kelvin. Joules per Kelvin will be the unit of entropy change. So if joules per Kelvin is the unit of entropy change, the unit of entropy also will be joules per Kelvin. So children, this much for now. We will continue in the next video, and we will try to find out the driving force for a spontaneous process. Till then, bye bye, have a good day.